Hardaway.
Cool. Thanks, Ari. Really appreciate you having me here. First, let me double check to make sure that sound is okay. I was having a little bit of an echo earlier. Cool. All right, I got a thumbs up in a couple of windows, so that's excellent. So let me share my screen and then I will get started and talk about what I'm here to talk about. And then could I get thumbs up again for, great, thanks. You know what I'm about to ask. All right, let's see, present. Cool. Well, as Ari mentioned, I'm Grayson Hardaway. I'm a security engineer at R2C, which I'll go into a little bit more about the company in a little bit. But today my talk is going to be about do-it-yourself Gosec, detecting complex code patterns using Semantic Grep. So thanks once again for having me. It's an honor to be here. And without further ado, let's get started. So the too long didn't watch of this talk is that writing secure code is hard. Static analysis tools are too noisy or too slow. Grep isn't expressive enough for trying to find insecure code patterns. And so what we need is something fast, code aware, flexible, powerful, and open source. And that's what SemGrep is. So SemGrep is a fast and syntax aware semantic code pattern search for many languages, which is an extreme mouthful to say. So an easier way to think of it is that it's like a grep, but specifically for code. So you can use SemGrep to do a bunch of different things, primarily search your code. You can use it to find security bugs, anti-patterns, whatever you want to search your code for. You can use it to guard your code. So you can integrate it with CI pipelines, block the build, notify if there's some suspicious looking code that gets committed. You can also use it to migrate off of like deprecated or older APIs as well. A little bit about me. My name is Grayson. I'm a security engineer at R2C. In a past life, I did a lot of interesting things for the US Department of Defense. But now I work at R2C, which is a San Francisco-based static analysis startup on a mission to profoundly improve software security and reliability. And so this is a snapshot of the team over here. And I want to take a second to say that none of what you see here would be possible without the great team here. So everyone contributes in a really unique way. Everyone here is extremely intelligent and motivated, and they're all really, really great to work with. So if you run into any of us in future, they're all great. A quick outline of the talk. First, I'll go over a little bit of background about SemGrep. I'll talk about grep and abstract syntax trees. And then we'll just do a bunch of SemGrep examples. So I'll teach it to you live, and hopefully the demo gods smile favorably upon me. And then I will talk a little bit about integration into CI/CD pipelines, and then how to get started with prefabbed rule sets. So you can write your own rules in SemGrep, but we also provide a bunch out of the box. So as I mentioned before, SemGrep is open source, which means that you can navigate over to our GitHub page and you can check it out. So the primary code or the primary language that SemGrep is developed in is OCaml, which is an old functional language. So our program analysis PhDs write in OCaml. It scares me to death. So for me, what I contribute to is the Python wrapper that we use to like instrument the CLI around it, which is much easier for me to deal with. So OCaml and Python are the two languages that we use. If you are interested in contributing, head on over there, check it out, grab an issue, whatever you want to do. SemGrep actually has an old history of being open source. So it's been around for more than 10 years at this point. The first iteration of it was developed at Facebook by this gentleman here. His name is Johan, and he joined R2C in July of last year. So he was the first static analysis hire at Facebook, where he wrote SemGrep. He has a PhD out of INRIA, and he was a contributor to Coccinelle, which is sort of a spiritual predecessor to SemGrep, but specifically for the C language. We support more than C. We support lots of languages. Go, Java, JavaScript, Python are our main ones. And then we have some limited support for other languages, as you can see here. And we're adding more all the time. So that's a little bit about background about SemGrep. Now let's talk about grep and abstract syntax trees. So Many of you may be familiar with this classic XKCD of trying to use regular expressions to solve a problem, and then regular expressions becomes one of your problems. I have experienced this firsthand, especially when it comes to code, where if you write a regex trying to find code, you might find like comments or documentation, or just it's a wild number of things that you never thought you would find, but you find them anyway. And so that's sort of my experience with grep in code for sure. And the reason that grep isn't always the best choice for code is that fundamentally code is not actually a string, it's actually a tree. So if you remember way back to like your compilers or programming languages class, at some point in the chain, code gets transformed into an abstract syntax tree or AST, which is then interpreted by the compiler or interpreter or whatever to produce the end result. And so there exist methods of matching on the abstract syntax tree. One such tool is Gosec, the security checker for Go. There are a handful of other ones, such as Bandit for Python, and others as well. Excuse me, one second. Sorry about that. I'm looking for the mute button and I can't find it. Hopefully the demo gods are nicer to me than the voice gods are. So I apologize. I appear to be losing my voice. Anyway, to continue, if you guys can hear me. Cool. So there exist a bunch of these. If you, oh man, sorry. If you want to develop for these yourself, then you have to become an expert in the AST of that language, which is a daunting task. So there exist some alternatives, such as some paid tools. The issue with those is that they can be, they're not very friendly to work with. They're hard to get data out of, they're complicated to set up, and they take forever to run. One second.
Hey, Grayson, we can be pretty flexible if you'd like. Would you like to go? Would you like Mofi to go first, and you can take a break and see what your voice needs, or do you want to continue?
I think it's okay. I think I just got to get whatever this is out. So
Go ahead and take your time and do that. Feel free.
okay, thanks. I'll be right back. Should be just a few seconds.
While Grayson is doing that, I did go ahead and I dropped the links for the AirPod raffle into the chat. And if anyone else wants to enter for the JetBrains license, please go ahead and do that. And I will add you so we can do a drawing after the talks are finished tonight.
I think I am okay. We'll see if this goes. Thank you for being patient. I sincerely apologize. Anyway, so to get back to where I was, there's grep on the left, there's AST stuff on the right, and SimGrep kind of lives somewhere in the middle. So it's an easy interface, but it operates on the AST of the program, so it'll actually parse it into an AST and then run the search on that. So the fundamental insight that SimGrep offers is that it lets you reason about your analysis the way that you reason about your code. And so you'll see very soon that the syntax for SimGrep looks a lot like the code that you're writing for. And so without further ado, let's take a look at a bunch of examples. So I'm going to go over some of the fundamental primitives for SimGrep, the ellipsis operator, something called meta variables, and then composing patterns together. Just a couple of advanced features, and then a bunch of Go specific cool examples. So let's say you're a developer or an AppSec engineer at a company, and your company's security policy has decided to ban RC4 from your code. So RC4 is an old encryption scheme. It's known to be breakable very easily. And so they just want to make sure that it does not exist in the code. So let's see. So I'm going to jump over here to a website called semgrep.live, or I guess it used to be semgrep.live, now it's semgrep.dev, but semgrep.live will still work. And this is a live editor inspired by regex 101, where you can type in a semgrep pattern here and write some code down here and see if your pattern matches what you expect. And so let's do this. Right off the bat, the easiest way to get started is just copy some code that you want to match and dump it into the pattern and click run. And so right away, we see that we get two matches. We get RC4 new cipher key and key again. And we can see that semgrep has some advantages over regular grep right away because it doesn't detect this comment down here. And if I could scroll down a little bit further, well, there's a string literal down there that also has new cipher in it, and it does not pick that up. And so semgrep lets you not worry about like white spaces, lets you not worry about new lines, any of that, because it understands the code that it's looking at. Instead of you having to like think about like, oh, might a human insert like a space here? I don't know. Like you can just write code that looks like code and it'll find what you're looking for. Now, we also want to detect this other key. And so the way that we can do that is with the ellipsis operator that I mentioned earlier. And the ellipsis operator works a little bit like dot star in regular expressions. But what it kind of does is it abstracts away sequences of things. And so in this case, it's basically saying there could be any number of things inside the arguments to new cipher, but we don't care what it is. We want to detect everything that is rc4.newcipher. And so now, as we can see, we pick up all of those, which is great. So that's kind of the ellipsis operator in a nutshell. The next example, let's say that you have a mandate to never use the library or the package that's called unsafe. Makes sense. So unsafe will bypass a lot of safety mechanisms in Go, hence the name. And so let's say you have decided at your company you're just never going to use it. So I'll go back over here to the live editor and we'll do the same thing where we'll copy this chunk of code, which has unsafe.pointer, and click run. And immediately we will see that we get unsafe.pointer, which is great. Now we don't get this one because it has a different name in here. And so we want to abstract that away with ellipses, which we've done before. Now we have both of these, but we still also want to detect this unsafe.sizeof. So we want to detect any method or function that comes out of the unsafe package. And so what we have to use here, you might think that you would do something like a ... here, but that doesn't work because there has to be a thing in that segment of the code. And so the way that we denote that is with something called a meta variable. And so a meta variable starts with a $sign and then all capital letters. And this can be any name that you choose in the same way that variables can be any name that you choose. But what this is saying is that there's like some portion of the tree here that we want to detect, but we don't know what it is yet. And so we can see we get it. What's that? I've certainly had smoother presentations, so thank you for bearing with me. So now let's say that we want to find insecure TLS configurations. And so the two things that are highlighted here are old versions of SSL, which are known to be broken and easy to break, and also this insecure skip verify set to true, which says don't verify the identity of the host. So it's like that. I think it's analogous to like when you SSH into a machine and it says like, this is the fingerprint, do you trust it? Basically, you're saying always trust it. So what we're going to do here is actually compose patterns together, because what we want to detect is a TLS configuration that has one or the other of these conditions. So the insecure version of TLS or insecure skip verify set to true. And so hope this works. Yep, perfect. And so in the SemGrep editor, you can add and subtract pattern clauses using this plus and X, using a set of Boolean operators that will let you compose patterns together. So you can OR patterns together. You can check and is inside, which is a range, and some others. Now, if you just say this in English, what we're trying to detect is TLS configurations where the minimum version is SSL 3.0 or insecure skip verify is set to true. And so OR is the operator that we're going to use. And so we will type that in here. Actually, I'll try to copy this in here and see if it works. And so now what this should do is also highlight this one where the version of TLS is okay, but insecure skip verify is set to true, whereas it did not detect this before. And I can verify by deleting that and clicking run, and it only detects this one. So composing patterns together ends up being extremely powerful for some complicated searches. So up next, I just want to glance over some advanced features. So I'm going to start out with autofix. So if we revisit the insecure version of SSL, I'm going to flip over to the editor. What we can do here is on this tab, there's a simple and an advanced tab. What SemGrep is actually operating on underneath the hood is a YAML configuration, which is what you see when you switch to the advanced tab. And there's a bunch of extra things besides simple pattern searches that are available to you in the advanced tab. One of those is fix-regex. This clause will let you specify a regular expression replacement. And so if you specify this, the editor will show you this slightly mangled helpful tip about what it's going to replace. And it's slightly mangled because I'm zoomed in a bit, so it's squished. But you can see that the version in the real code is SSL 30, which is what the SemGrep pattern detects, that we want to replace SSL 30 with TLS 1.3, that the autofix over here has applied that. And if we click apply fix, it'll just do a replacement in line for that, which is super cool. And so this is useful for migrating off of old APIs or deprecated APIs or similar situations. The next advanced feature that I want to talk about is message interpolation. And so one feature of meta variables is that they also sort of capture the content of what they detect, similar to capture groups in regular expressions. And so one of the keys in the advanced tab is a message, which is what will get displayed when the finding is detected. And something you can do with meta variables is interpolate the meta variables into the message. And so one of the guys on our team came up with this idea of detecting routes in a web application by using a SemGrep pattern and interpolating the values into a comma separated value. And then when SemGrep runs on the command line, it'll spit out all these CSV lines that we can then check like the entire surface area of an app. And so as an example, this is the Gorilla toolkit where it's adding a bunch of handler functions. And so if we just run this really fast, we'll see that we'll detect all of these, and that the messages will give you the endpoint of the endpoint that's exposed, the method or function that's called, and the HTTP verb that it picks up. And so we have used this to do something like this, which is actually a Flask route, but doing something similar. where we'll grab all these attributes of the code, spit them out into a CSV file, and then feed them into a visualization. So this is a Flask app where all of the routes are demonstrated within whatever files they happen to be inside. And so we've used this on consulting engagements when we go in and review other people's source code, where we'll just like get a snapshot of their entire exposed surface area. And then the additional helpful detail here is that the dots are color coded with the level of authentication that's required on that route. So green is admin, yellow is normal user, and red is anyone can access that route. And so it gives us an extremely useful starting point for determining where to check, because if it's a red route, then anyone can access that, which is the more likely attack vector. So now I'm just going to demonstrate a bunch of examples. So these are a bunch that I pulled out earlier today that I thought would be interesting. And so one of them, you can use Semantic Grep to enforce the order of method calls or function calls. So this is probably more useful in older APIs that are designed in such a way that you have to like call a function before another one. But let's say you've inherited a code base like that, you can enforce that here. And so I just want to glance over this one really fast. So this pattern says, find me any method where make transaction is called, but then filter out and is not any method where verify transaction is called before make transaction. So if you can imagine, this is a financial application. You want to verify your transactions before you make them, because if you don't, that might be bad. And so if we scroll down here, apologize for the small window, you can see immediately that this is detected because it doesn't have verified transaction before it. This one is also detected because verified transaction occurs after make transaction. And so this ends up being pretty cool because it demonstrates sort of the expressiveness of what you can do with Semantic Grep. The next example is inline string regexes. So you can use it to do things like detect HTTP. So I'm not going to go into the editor for this one. I'm just going to demonstrate it here or show it here. So let's say that you are making a call to HTTP. This will obviously happen over a unencrypted connection. And so you can do this thing where you specify like a string literal with this strange looking syntax, but it just means a regular expression. And then identify your string pattern here. And Semantic Grep will be smart enough to detect when this code is matched along with this string literal that meets this condition, which is kind of neat. You can detect imports, so pretty easy to do. Let's say you wanted to detect text template and forbid that in your application because text template doesn't do HTML escaping, and so it might expose you to cross-site scripting vulnerabilities. You can do that very simply just by saying import text template, and it'll pick this up, and with more after or before. And then the last one that I want to demonstrate here is sort of an approximation of data flow. So Semantic Grep meta variables, as I mentioned, operate a little bit like capture groups. And so what that means is that you can kind of use them to approximate like tracking information through a program. And so let me highlight this pattern down here. Let's say you wanted to detect any like a template that has been formatted using some string format method. And so this could be dangerous because if the string or if the template is formatted with user data, then it could be a security hazard. And so what this pattern says is use this meta variable string when the right-hand side of the equal sign is format.sprintf with any arguments. I don't care what it is. There could be some code in between here and there. I also don't care what it is. And then a writer object has the write method called with this stir variable. And so these will be enforced to be equivalent, which means it'll be tracked approximately through the AST. And so it will detect something like this above example where you have a string template where somebody inserts directly into it some potential user controlled data, and then that data eventually ends up being rendered. And so it will detect this segment here from rendered all the way down to w.write. So that's a quick overview of SemGrep, a lot of demos, a lot of examples for what you can do with it as far as writing patterns go. I want to talk a little bit about automating it. So SemGrep is available as a binary, like on the command line. It's also available as a Docker container if you want to use that. But its real power is when you begin to automate it. And in particular, it's when you automate it by including it in a CI/CD pipeline. So we have support for a bunch of different things, including GitHub Actions, GitLab, and any other things that you see here. If your CI/CD pipeline of choice is not included, it's relatively easy to add because it's so lightweight. It operates just like a binary you would expect on the command line. And we feature JSON output, which makes it easy to integrate with other systems. We have other outputs as well. So we want to make it easy to plug and play rather than difficult because, well, that sucks. So here's an example of SemGrep running on our code in a GitHub action. And so this is just kind of what it looks like. But what I want to do is zoom in on the particular finding that we had. And so this is kind of what the output would look like, or does look like. And the finding that it detected is something called Python Flask Security Injection Path Traversal Open. And so that's a mouthful, but what it's saying is that it detected a path traversal in one of our Flask applications. And this is great because this never went to production, obviously, because we had a SemGrep rule in place blocking this behavior from being committed to the primary code base. So this is like a huge win because this is exactly what we're hoping to accomplish with SemGrep, is to codify domain knowledge and automate that in such a way that if we've decided we never want this code pattern in the code base again, then we could do that by using that rule in a CI/CD pipeline. So I've talked a lot about writing rules. There are also a lot of rules that are freely available, to include the one that I just demonstrated or just showed you on this slide. And they're all available in our registry. Now, the registry is open to everyone. Anyone can contribute. We have a lot of community participation already. A couple of our biggest contributors are the maintainer of Node.js scan. So he's written a bunch of JavaScript rules for us. And also a gentleman named Damian Grisky has written a lot of Go rules that ended up in our registry as well. We've ported select rules from Gosec and other security tools. And then we have a bunch of ideas contributed by a lot of other people. And then a special mention to some independent security researchers that we have who basically full-time go find cool bugs and then like write SemGrep rules for them. So those are always wild when we get those. Yeah, here's a demo, some of the rules that Damien has written. If you want to use the rules from the registry, it's very easy to do. All you have to do is point SemGrep at a URL that the registry provides. So it's as simple as installing SemGrep and then saying SemGrep --config some URL in the registry. And so if you wanted to run the Gosec rule pack that we have, all you have to do is say SemGrep --config equals this URL, which will download all the Gosec rules that we've ported and run them on your code. So near the end here, some stuff that's coming up soon is improved language support for our alpha and beta languages. Some new languages, Kotlin is the next one that's on deck. Development for that will be starting in a week or two. More rules are always being added. And we're also starting on something that we're calling prevention cheat sheets. And so there'll be really detailed cheat sheets that show like code examples of things that you should not do in order to avoid common security problems, such as cross-site scripting, and other ones as well. We are working on something that's called SemGrep Community, which is a place where you can centrally manage your repositories. So you can create sets of rules that you then apply to different repositories, and it will just automatically handle it all for you. So instead of going in and setting them up all manually, you can do it all here to make things a lot faster. We have a VS Code extension that's in beta. And then something I'm excited about is generic patterns. So we have primary support for a lot of languages, but we're adding something in that will sort of approximate a tree for any language, which I'm really excited about. So it's SemGrep lives kind of between ASTs and grep. This generic pattern will live somewhere between like grep and SemGrep. So it's like a quarter of the way there. Anyway, that's my talk. So if you want to get started with SemGrep, you can do so pretty quickly. Just install it, run it on a config, or you can check out the online editor, which I was using throughout the presentation. Email me if you have any questions. You can also tweet at us. You can join our community Slack. And if you feel so inclined, please consider taking the survey at the bottom. We value your feedback. And we use this data to determine sort of like what we are going to work on next. So that is everything for me.
Awesome.
Thank you, everyone.
Grayson, thank you so much. I really appreciate that. I think you may have already addressed, it was a great talk, by the way. I think you may have already addressed one of the questions that Anthony asked about the LSP used by tools like VS Code. Did you address that, or did I miss that?
I did not address that, but it is actually being worked on. So Johan, the guy who wrote SemGrep, is really interested about LSP and integrating that, and so he's been working on trying to figure that out. So he had a working demo like a week ago, in fact, but I haven't seen any more progress other than that.
Okay, well, that's good to know that's coming. Does anybody else have any questions? And in the meantime, Grayson, if you don't mind going ahead and passing the host over to Mofi so we can get started. But while we're waiting while Grayson's doing that, does anybody have any questions for Grayson that he can answer for you regarding his talk? If you prefer to put it in the chat, we can read it to him there. Or if you'd like to just unmute yourself, please do.
I do see a question from Prakash, which is, oh, it was to me. I see privately, but he's asking about the slides. I'll post the slides. I'll do that here in just a few minutes.
Well, hopefully Prakash said some nice things to you. That's what we hope.
Yes.
That's awesome. Well, good deal. Well, hey, Grayson, thank you so much. And again, Grayson, how can people reach you if they have any questions? Are you, do people follow you on social? Do you prefer email? What do you prefer?
Yeah, I don't, I have a Twitter that I've never tweeted out of. So,
awesome.
So you can email me at grayson@r2c.dev. That's probably the best way to get a hold of me, or you can get a hold of me in the community Slack. It's pretty active there.
Okay, cool. One last question from Mark. What's the scariest thing about OCaml?
It's very runic, and I'm not sure that would even make sense unless you've looked at it before. But the things that I'm kind of used to seeing in normal, well, I say normal, in the programming languages that I'm familiar with, they just kind of don't exist in OCaml, or they're very different. So there's some cool things like the match syntax, which actually Python is building into their language, which I'm really excited about because I really like that. But otherwise, yeah, it's just hard to look at and hard to read. Yeah.
Yep, that's I think that's why it's classified in Wikipedia as it is, as from a language perspective. It has some use, and it's filed appropriately. Hey, Grayson, thank you so much for coming out, taking of your time to share with us tonight. I know that was really valuable for a lot of us. And if anyone has any questions, don't feel free to reach out to Grayson like he asked. And thank you again. At this point,
and thank you all.
At this point, I'm going to go ahead and turn this over to Mofi, who's got has got a great talk for us prepared. Mofi, you probably don't need an introduction, but at the same time, I'm going to let you go ahead and speak about yourself and share that. But thanks again for preparing a talk for us this evening.
I think my screen should be sharing right now. If you can, for some reason, I don't see anyone's faces. So let me do that. Try to get some of the faces back. Excellent. And I will bring that out this side. Here it is. And I moved it here. Well, how is everyone doing? I mean, again, the people on the video, you can just probably nod to let me know that you can hear my voice. And it's been a really long time. I haven't met or seen any of you for such a long time. The Golang NYC Meetup last year, we were just getting to a stride. Then things happened, as you may know or may not know if you're not living under a rock and living in ignorant bliss. But we have not been able to meet. But again, I'm glad that Ari and Gray took the initiative to bring this back. And thank you, Ari, for taking the time and putting all this effort to make this happen. So my name is Mofi. I'm one of the co-organizers of the meetup. And this month's meetup, I thought I wanted to share a talk that I've been working on over the summer. Presented it as a 3-hour workshop in O'Reilly learning thing, but tried to condense that into a 30-minute talk for everyone. If you are familiar with Go quite a lot, if you've been writing Go code and concurrent code, this talk might be a little too on the rudimentary side, but hopefully there's some couple of learning or a couple of refreshers there for everyone. And let's get started. So if you want to find the slides, if something is interest, the slides link is in this slide, which is super meta, I understand, but you can just take a picture, find this link. The slides are in this link. So it is tiny.cc golang-nyc-concurrency. So again, we're going to start off with the easy topic, concurrency.
Hey, Sophie, I'm so sorry to interrupt you. Because you're the host, you are in charge of the waiting room too. Could you let William in?
Yes.
All right. I appreciate it, man. I'm so sorry.
Absolutely. Well, I am just trying to get the number to 35, as you said.
That's true. I don't know how many drinks I need to drink
Actually, we just made it. We just made it. So you wouldn't have to.
Good
yeah. So, okay. So we're going to talk about concurrency. And concurrency, what is it then? If you already know, great. If you don't, I'm going to tell you. It's a process occurring simultaneously with one or more process. It is a composition problem. So what does that even mean? Because this definition only makes sense in comparison when you're talking about parallelism. So let's just jump into that right away. So parallelism is the idea that simultaneous execution of multiple entities of some kind. And that entity in our case is code. In real life, it is, let's say you and your friend are both stacking paper. So you're doing work parallelly together. So concurrency is a property of the code. So we write code that can be concurrent. Parallelism is a property of the running program. So far, even I'm reading the slide, I don't understand what that means because, okay, it's a property of the running code and one of them is a property of the running program. Great. So the one thing to understand in the Go ecosystem or programming ecosystem in general, concurrency is not parallelism. And you'll see this quote is taken from Rob Pike's talk in Go for Fest 2015. A lot of the Go proverbs were taken from that talk because that talk was literally called Go Proverbs. So it's one of the quotes from Rob Pike himself. Concurrency is not parallelism. So the reason concurrency and parallelism has some differences is that as humans, it's almost impossible to think parallelly because we always as I'm speaking, I'm moving my hand, but that's not thinking parallelly. I'm just doing two things that are completely unrelated to each other. So we write concurrent code usually and hope that they would run in parallel. What I mean by that is that let's say I wrote an application and I just run 2 copies of that application. My application itself is not running parallelly. I'm just running 2 copies of that application. That's how I'm getting the parallelism, not by the code itself. There are some programming languages that you are allowed to write parallel code, which are really obscure, really difficult to understand. I tried reading code there once, tried understanding from a video. My brain hurt afterwards, so I gave up and moved on to languages that makes concurrency easier, like Golang. So my name is Mofi. I work as a developer advocate for IBM. I mostly do container stuff, collect stickers, and write Go code. And you can find me on the social at MofiCodes if you need me to. My email address is also moficodes@gmail.com. So if you need to email me for anything, you can do so as well. So I'm going to start this talk with a question. How quickly can we download 3,250 images files with the total size of about 1 gigabyte? Right? So the number, it's not an arbitrary number. I actually have object storage bucket with that many images that I hope to download that many images from. So what I have here is cd naive, cd data, and cat images URL, and word count -l. So I have a file that has 3,250 URLs. I can do less image urls.txt, and it has a bunch of these images in this. And each of those images are about few hundred kilobytes in total. The entire folder would take about 1 gigabyte of space. So how quickly can we download all these images? That's the question I'm starting with. Now, writing image file downloader in Go is not that difficult. So I have done it here. So if I were to open that particular file, you would see I have this file. It loads up all the URLs. Then for each of those URLs, I go and download that file. So let's try running that, because I would need to, this will take some time. So I'll get with my talk as this downloads. So I'm going to say time go run main.go. And I'm just timing it so that when we come back, we can know exactly how long it took. So it's going to go back ahead in the background and start downloading this file. As that happens, let's continue with this talk. So in this application that is right now running, it's running on a sequential manner. It looks at each file, goes to the network, downloads the file, writes to the disk, goes to the next one. So I'm running my code right now in a sequential manner. So obviously, most of you know, this application will be obviously slower than any application that I would write later on. So let's talk about how can we improve this application. So what are the Go concurrency primitives that we have access to make our application faster? So very first thing is Go routines. If you want to run concurrency in Go, you create something called a Go routine. It's one of the simplest way you can do concurrency in any languages. All you have to do is put the keyword Go in front of any function. That function then becomes a function that executes in concurrently with your main Go routine that is running in your main function. So if I were to run this, it wouldn't actually print anything, because my main thread of execution is going on while this goes on the separate Go routine, and my code will exit at this point, and it will just go out of context and it will not execute anymore. So if you want for it to wait, if you want to wait for the result to come back, what you can do is use something called a wait group. So wait group is a synchronous counter that works across threads and Go routines. And what you use Go routine wait group for is make sure your Go routines wait, your main thread of execution wait for the Go routines to exit. So wait group have a couple of things. So wait group lets Go have a fork join concurrency model, and it's a thread safe counter, as I said earlier. So wait group has three main things. Adds a number to the wait group. Done adds -1 to the wait group. And this is crucial. It's not subtract 1. It adds -1 to the wait group. And finally, waits for the wait group count to be 0. Now, for some reason, in the end of your program execution, what if add and not done not equal to the same number, right? If add and done are not equal, what can happen? So if wait group count is greater than 0, in this example, that would happen. For example, you add 2 to wait group, call done once, and call wait. That would result in a deadlock. And deadlock is a situation where program cannot go anywhere, just stuck in that place. The reason it deadlocks because, first of all, we added 2 here. We did done once, that added -1 to wait group. So it's now at 1, and wait group now is at 1. You will wait forever. It will never go to 0. Your code deadlocks. What if wait group count is negative, like negative number, less than 0 at any point? So for this example, you have added 1, called done once, called done again. So I added -1 twice. So at this point in code, your wait group is a negative number. That would immediately panic. So again, 0, -1, which will panic. Your code will never reach this line. So you'll never actually wait. Your code will immediately panic. So I just gave a word called fork join. What does that mean? Fork join is the idea that you have a main thread of execution. You create a new Go routine that forks a process. If it's kind of like old Linux words, like forking a process. So you have a child process. Again, process is not the right word here because it's a Go routine, but you can imagine as a process that is doing its thing. And at some point, this child process finishes its work and then joins back to the main thread of execution. So again, and this child ceases to exist whenever it's finished doing its work. couple of other things like mutex and read-write mutex. Mutex is a way you can control how many things can access something. So mutex is a way to control access to things. And this thing could be anything. Usually you are basically stopping access to data, any data that is shared across multiple things. So mutual exclusion lock, that's the full meaning of mutex. And zero value for a mutex is an unlocked mutex. An unlocked mutex is something where you can take access to the object the mutex is locking and then lock it while something is holding that thing. Once they're done using it, they will give back, unlock the mutex, and someone else can go in and access it. Read-write mutex is a special kind of mutex where you have a special lock for reading and writing. For example, if you have a data object that gets written very often, not very often, but read quite often, you probably want to opt in for a read-write mutex. So mutex for anything that needs to have synchronous access, read-write mutex is useful if you have something that has a lot of reads, but not as much writes. Then you have a primitives called condition. Condition is something that makes your code wait until a condition is satisfied. So it's implemented a condition variable. So you have a variable, your code will keep on waiting until that condition becomes true. Do I have someone? Okay, I have one more. Here you go. So condition have two different things it can do. One is signal, one is broadcast. So you can use signal to let one go routine know that the condition is satisfied. You can use broadcast to let every single thing that is waiting on that condition know that the condition has been satisfied and it can go ahead. You have another thing called once. All of these things are part of the sync package in Go, by the way. So you have this once. Once is something that only gets executed once, no matter how many times they are called. When I first heard about once, I was pretty confused, like, why is that something a thing and why we need this? Then I tried to search for once in the Golang source code. This once function has been used close to 100 times in the Go source code. So that's actually pretty important. I didn't think once would be that useful, but it is apparently. But usually when you're writing code, the reason they need to do once is because they're initializing a bunch of things in the runtime. They need to make sure it happens only once. Usually when you're writing code, you probably won't need to use once ever. But if you need to, it's there, you can use it. Then you have pool, and pool is nothing to do with concurrency itself. It's to make sure you have a set of resources that you don't want to reinitialize over and over. You just want to create a set amount of them at the beginning, and every time you need it, you can just get it off the pool rather than recreating it. A good use case for it would be like anytime you have a database connection, you don't want to recreate that connection over and over. You just have a connection pool. Most database libraries already have that built in, so you don't really have to recreate that yourself. But if you're creating a database library or you're using some sort of thing that you're not using a library for, you're just writing it yourself, pool is a good use case for that. So again, set of temporary objects that may be individually saved and retrieved. So you have this collection. And once you create them, you don't have to recreate them over and over. So all these things come from the sync package, and all these ways of doing concurrent things in Go are also pretty much available almost every other languages that are out there. Now we're going to talk about some of those things in Go that are not necessarily like only available in Go, but that's one of the core strength of Go concurrency, and that are channels. So channels is a way where one or more Go routine can talk to each other back and forth. Channel is like, so if you're familiar with the CSP style of concurrent programming, where communicating sequential processes, channel is that implementation of that idea. So you have this thing where you have a one Go routine that is passing information to another Go routine via some channel. So channels are typed conduit through which you can send and receive values with the channel operator, which is this arrow. And yeah, it's funny because in the definition, we use the word conduit, which is literally a synonym for channel. So it's not necessarily a different definition, but here we are with computers. We're bad with naming. So channels are typed. Channels can be sending, receiving, or both. Channels are blocking. Each send must have a receive. So every time you're sending something in a channel, one Go routine sending something to another Go routine, you would have to have someone on the other side listening for the data coming in, so that they can receive it. Otherwise, your Go routine will be blocking for that channel send. And you also have the idea of a buffer channel. So buffer channel is a blocking channel too, but it can be non-blocking to some capacity. So if you create a buffer channel of size 10, it is non-blocking of up to 10 cents. After that, it becomes blocking again. And so this is, again, another quote from Rob Pike. So channels orchestrate, mutexes serialize. So if you're writing application that you want to have some concurrency, but at certain points you want to serialize your code back into certain sync points, that's where you are probably using something like mutex to serialize your code back. When you're using channels, you're not necessarily trying to like find points in your code where you're gonna synchronize every single point. You're basically trying to let everyone have information when they need it and how they need it. And this is a handy-dandy chart you can make use of when you're trying to use channel with each other and what kind of operations you can take against each other and what will happen if you're taking that action. So if you're trying to read this, it's going to read on the left column, you have the state of the channel right now. On the top row, you have what is the current state of the channel. And then on the middle, you see what happens when you try to take that action. For example, if you have a channel that is nil and you try to read from it, that will be a block. And same will happen for a write channel. So if you try to do a write on a nil channel, that will also block. If you try to close a nil channel, that will panic. So there is 3 cases in channels that can panic. So you have to be very mindful when you're using channel. One of them is writing to a closed channel, closing a closed channel, and closing a nil channel. So these are 3 cases where it can panic. There are 3 cases where it does compilation error. So this one you don't really have to worry much about. If you write a code that hits any of these cases, your compiler or your IDE, depending on what kind of IDE you use, will tell you this is not a good piece of code. And these ones make a lot of sense if you read through them. The state is receive only. If you try to write to a receive only channel, obviously that's going to be a compilation error. If you try to close a receive only channel, that is also a compilation error. This one is a little bit interesting because why is closing a receive only channel a problem? It's because you don't want to close a receive only channel because a channel's nil value should be useful. You only want to close write channels because the person writing to the channel should be the person closing the channel. And finally, if you're trying to read from a write-only channel, that's also a compilation error because that doesn't actually make sense. You also have a select statement. So select lets you take action on multiple channels at the same time. It's like a switch case for channels. So go select lets you wait on multiple channel operations. So select lets you actually orchestrate your code in such a way where you have multiple of these channels and you can wait on different condition. Whatever channel gets the data first, you can act on that data. This is one variable that is available in Go. Since Go 1.5, Go max procs automatically gets set to the number of CPUs you have available in your Go machine that you're running on. Before that, it used to be set to 1. But you can set the Go max procs value to select how many Go routine thread should start. So how many process Go should start when you're starting up a concurrent application. You have, okay, so yeah, so this is a variable. You can set the value yourself, but by default, as of 1.5, it is set to the number of CPUs you have available in your machine. So you don't really have to worry about that particular variable anymore, but it's there if you want to tweak with it. Context. So context, again, is another package that is not necessarily anything to do with concurrency itself, but context gives you some special powers, things like cancellation, deadline, and timeout, and things like that. That is super useful when you're running a lot of concurrent application, concurrent functions that you don't know when they're going to end, and you don't want them to just like continuously running. So if you want to have some sort of deadline or some sort of way from a central location to be able to cancel those, context becomes very useful. And this is another quote from Rob Pike. So don't communicate by sharing memory, share memory by communicating. And before I continue on, so I basically talked about all the different primitives you can have in Go. That's like, there's about like 10 or 12 different things. That's literally all of them you need to know to be writing concurrent code. So at this point, we can say, you know what, let's move on. We're all gonna write great concurrent code and our application is gonna be faster. But that's probably not the case. We need to kind of look at examples of how they actually do. So let's go back to the sync package one more time. We talked about a few of those. So let's look at wait group. So the code example of wait group would be, so you have this main function. I'm adding 2 to my wait group. I have 2 function calls. One of them is a function that I'm calling here. One of them is an anonymous function here. And I will wait until both of them are done. So I can go run main.go. As you can see, I will get hello function, hello closure, and I will print out the number of Go routines at the end. So at the end of my function execution, you will see I print number 1. That is only my main thread of execution. If I did not have this wait group wait, what would happen is I will basically just fall through. My code will not print anything, but at this time, at my runtime, I have 3 Go routines executing, which none of them could finish because I didn't wait for them. You can also look at the conditional. So conditional is a little bit more complex to understand, but if you want to very easily understand that, you have a broadcast. Well, I'm not gonna spend the time to, example is gonna come back in a second. So let's look at a mutex instead. So with mutex, what I'm doing here is I have this number of, let's say 10,000 times, I'm gonna increment my value here. And after 10,000 times, I'm gonna try to print whatever value I have. I'm spinning up about 10,000 Go routines for D, but I am not controlling access to that variable. So let's see what happens if I were to do that. Not wait group. And if I run this, you'll see I print about 9,460. I can run it a few more times. Every time I run it, I'm going to almost get a random number in the 9,000 range. It's because, again, as this data is being accessed, someone else also reads the data and increments this value, which is done here, and writes it back. So for some of my about 100 or 1,000 of them, they overrode each other. So the value actually didn't increase. So this is the race condition you will see. So if I were to run go run -- race main.go, so the race detector in Go, it will actually tell us that in line, however many, whatever line it is at line 36. So in this line, when I'm trying to access the data.value, I have a race condition because I have more than one Go routine trying to access that variable to increment that value. So to fix that, we can make use of a wait group and increment this by adding in, let's figure that part out. So hold on, and I will need to also uncomment this one and comment this one out. So if I were to run this now, well, this still has a race condition because I am waiting for the result to come back, but I'm actually not solving the actual problem we are initially seeing. The problem was I'm accessing this variable. More than one Go routine is accessing this variable. So the way to fix that is using a mutex. And comment this one out. Well, comment this one out and uncomment this one. And comment this one and bring this one in. Okay, so if I did everything correctly, oh, this is going to be an error too. Uncomment that. So in this case, what I'm doing here is, oh boy, that is not good. Oh yeah, I have to change this one because so I have to have a mutex that is the one that is going to control access to my data variable, which is value. So this value, I'm going to use this mutex to control access to this value. So if I run this now, you would see that I print out number one, I print 10,000 and it still found a data race. That is unfortunate. What is the data race here? Line 33. Oh, so this is the data race here. I'm trying to print this value. We don't have the mutex. So that is not necessarily a problem we need to fix. All right. So let's actually try to go back and see when we ran last time and what was the printout for our time function that we ran. Here we go. So my download finished. It took about 4 minutes, 54 seconds. So this is the question I asked in the very beginning. How quickly can we run this function to download 3,250 images? So it took about 5 minutes to download that many images, which is quite fast. But if you look at in this space here, the time I used to actually do the download was 19.45 seconds in the user space and about 10 seconds in the system space. So about 30 seconds was actually used to do the work, and about 4 minute 20 seconds was used to just wait for things to either go talk to the network, download, then write. So all this time was wasted in trying to download this image. Now, since we have learned all these cool new like concurrency things like wait groups and mutex, let's go use it and try to download it much faster. So the one we're going to try to do is use wait groups and spin up all 3,250 image download at the same time and see what happens. So what I'm doing here, I'm ranging through all the URLs that I have loaded from this data file. And for each of those URL, I'm going to just run this go routine that's going to do a download file to them. So immediately you can probably finish that in like less than a second. Maybe let's try that. So downloader and wait groups. OK. So time go run main.go. So I run this and it's downloading. Oh boy, I get errors. Why do I get errors? I thought go routine is going to save my life, but it didn't do anything. So the problem here is go routine are very lightweight. I can spin up hundreds and thousands of them in the same machine without breaking a sweat. But the problem is, in most time, when you're spinning up go routine, you're going to get bottlenecked by something else. In this case, what am I getting bottlenecked by is actually how many network connection can I open in a machine, right? In a machine, if you try to open 3,250 network connection at the same time, the network IO of that machine will be like, I can't do this. So it's going to just give up. So we have too many open files of network socket connections, and it just didn't let me finish it. So in total, we spent about 6.7 seconds. But let's see how many images actually we downloaded. So cd images, ls, -1. So we downloaded about 2,800 images. That's not too bad. But we started off by trying to download 3,250 images. We only managed to download about 2,800 of them. And after that, it just gave up because it couldn't open any more file pointers. So let's improve that a little bit by using the wait groups buffer. So when you're spinning up go routines in Golang, oftentimes, again, if you have a bottleneck somewhere else, just like this one, what you would end up have to do is control how many go routines you actually spin up any given time. So we still want to spin up 3,250 go routines in total, but we want to control exactly how many of them we let spin at the same time. So the way we can do that, in this case, we can use something like a buffered array that keeps track of how many go routines are running, and we only let more go routines spin up if that number goes below that number. So in this case, what we're doing is we have a routine limit and we have a buffer array. And if the routine limit and buffer array are the same size, we wait. When that changes, we can do the other thing. And whenever that number changes, we can signal. So the conditional that we were using before, we can signal to let this condition know that the condition has changed. Now you can try again and run the go routine. So in this case, we're going to run go routines again on that. Once the number of buffer channel size goes below the number of total routine limit. And I'm making arbitrary decision that my routine limit is going to be 5 times the number of Go max procs that I have in the system. So this is a machine with, I think, 16 CPUs. So my max procs is 16. So I'm saying any given time, I'm going to spin up no more than 80 Go routines. So wait groups buffer. And if I run time, go run main.go, and we're downloading again, it's going to take some time. And in about 4.68 seconds, I downloaded all the images I wanted to download. No error, so that's good as well. So let's test if I actually got all the images. So ls images, -1 images, and word count dash line. And we downloaded all 3,250 images. And that is about 1 gigabyte of download in about 4.68 seconds. So this is the style of concurrency you can use if you are more familiar with the style of concurrency in languages like Java and other languages that have like these mutexes and wait groups and things, wait group like things. But in Go, we boast very heavily about channels, and Go has an idea of pipelines. with channels, you can pretty easily create pipelines. So let's see how we can do the same thing with a pipeline. So very first thing on a pipeline, in this case, this pipeline is nothing with concurrency. This is just the structure of a pipeline. What a pipeline is, output of one function becomes the input of the next function and keeps going until we're done. So what we're saying here is we're going to create a function that is going to first take all the URLs, and for each URL, start the download file. And once you have downloaded the file for each of the download, then we're going to call the write file content. And once we are done, that finishes the pipeline. So we start with the list of all the URLs, and we download one URL at a time, and you keep going until we're done. So pipelines, basic, and time, go, run, main.go. So this one is not doing any concurrency. So this is going to be pretty slow. So what I have done in this case, I actually made the image URLs like 20 images instead of 3,000, because it's going to take another 5 minutes, which I didn't want to take. So again, this is quite simple. So the next one we can do is spin up, again, as many go routines as we want in a pipeline. So we don't stop. We basically immediately start all the go routines, and in a pipeline, they keep downloading as they can. So if I could go back and pipeline and select, again, this is very similar to what we did earlier when we spun up all the go routines at the same time, but doing in a pipeline system with the channels. So time, go, run, main.go. And this would more than likely fail, because again, I'm spinning up about 3,000 go routines, and each go routine will then try to open a network connection, which will eventually run out of how many network connection I can open. Sometimes it will not even fail. It will just block. Your computer will basically just freeze. And you can see that happened in this case. If I do a htop, you'll see like some of my CPUs are at 100% usage, but nothing else is happening. My computer basically is not doing anything with it. If I go back here, it will just be stuck here. And if I go and look at how many images I downloaded quite a few, but I don't think I'll ever finish downloading these images because my computer just froze. So that's another thing you have to be mindful when you're using go routines to do something faster, is if you exhaust the resources that your computer relies on by spinning up way too many go routines, you might end up in a situation your computer can't even function because you just have too many things trying to do too many things. So in this case, this is never going to actually finish. This is going to continue running. And last time I tried, after 15 minutes, it timed out. So in this case, let's go back and try the last example. That is going to be pipeline with semaphore. So if you're not familiar with the semaphore is a way where you can control, just like a buffer channel we used. Semaphore is a way you can control how many things access to a certain things. In this case, our access is how many go routines we want to run. So you're using a semaphore to control that. So a semaphore in this case would be this example. And we have this channel, this download semaphore, and the file write semaphore. So Golang does have a semaphore library that you can make use of. But in this case, I'm just using a buffer channel. When the buffer channel is full, I'm not going to spin up any new go routine. When they're not full, I'm going to spin up new go routines to do them. So time, go, run, main.go. And this one should download all the images in about 4 to 8 seconds if everything goes well. So 5.9 seconds. So from 4 minutes, 54 seconds, we can bring the time down to about 6 seconds by using the Go concurrency primitives. And the code itself doesn't become too complex from where we started off, right? Our functions are still the same. We're just using the Go primitives in the order we want to use it in. So we're pretty much running out of time, but let me just jump to a couple things that I wanted to really talk about. Is we have the live logs, dead logs. There are a bunch of things that you want to learn, but as we go deeper into it, this is we probably wouldn't have time to go into all of them. But the one thing I want to talk about, some considerations, right? If you're interested in using concurrency in Golang, Golang definitely has concurrency as a much easier thing to get into for most people if you're coming from other languages. But few things, when should we not use concurrency, right? That's like a big thing, because everybody in Go in the community keeps saying Go is great for concurrency. But I'm going to try to kind of convince you there are cases when you probably don't want to use concurrency. So number one, some questions to ask yourself when you're like trying to solve a problem with Go. Number one, would a non-concurrent solution be good enough? Like if you're building a web application or something that has a lot of users, a lot of usage, concurrency is not going to make that usage go down. What it's going to do, if you have a lot of usage and every single usage of them are being executed concurrently, you might overload your system. So first thing is, if you just write the application in a synchronous manner, it's easy to understand, easy to run. Would it be good enough? If it is, let's move on. Next is, would horizontal scaling make more sense? Can I just run multiple copies of the application without actually making each of the application concurrent? And would that make sense? So it could, if that makes sense, also you can rely on that to make your application faster. Finally, can we optimize other things, right? Before you jump into rewriting all your application in concurrently, is there other smaller wins you can get before you start writing your code differently than what you are doing now? Some tips. Number one, don't try to think of a problem concurrently. It's very difficult. Parallelism is almost impossible. Even concurrency is difficult to sometimes wrap your head around. So number one thing you do is solve the problem synchronously and then find bottleneck if concurrency can concurrency improve the situation. In our case, when we downloaded all that images, we saw about 70 to 80% of the time was actually spent in waiting for things to happen. So that's a use case where concurrency definitely would make lives easier. So at any point we need to synchronize, it becomes a hidden bottleneck. So as you're running your code, there are points where you need to synchronize your code. Each of those points will become a bottleneck. So sometimes it is better to re-architect your system to make sure that you can remove those bottlenecks. For example, one of the use case we were trying to solve is we have a system that was writing a lot of logs to a file, and bunch of these processes were writing these logs to a single file. So every time someone tries to write something, they had to get access to that file. So that file was our bottleneck. So we went back and changed it so that each of the processes writes their own log file, and every once in a while we would write a separate process that combines all those files into a single file. Thus, we actually got rid of a lot of the bottlenecks, bunch of files where bunch of processes had to write to a single file. So Go routines are cheap. Use them freely, as many Go routines as you need to. But most times, the problem you'll face is not Go routines. It's going to be the limitation of your system itself. Like how many database connections can you open? How many network IO can you open? How many files can you open? Things like that. So they will be a bottleneck way before Go routine will be. And finally, thank you. I think there are a couple of chat questions or comments. Let's see. There you go. So I have one question. Haha, we are all under a rock now. That's true. And next is, okay, next one is this network IO available? File handlers, that is the blocker here. Yeah, so that, and I saw an error earlier that was, I couldn't open any more file handler. That was, yeah, that was not the network IO at that time. At the time, the problem was the file IO. But again, earlier when I tested, the problem was the network IO because I had too many socket connections open. In this case, I saw in this example, I saw the problem ended up being the file IO. But in either case, you will see your system bottleneck will be much faster to show up than your actual Go routine bottleneck. Go routine are way lighter compared to a thread. So if you are coming from a language, or if you're used to a language where threads are a thing, spinning up a new thread, switching context between threads are a lot more costlier compared to Go routines. So if you're building an application using Go routines, your consideration actually will be about the system limitation before the Go's limitation with Go routines are. A couple of other points. So if you're thinking about using Go, but you're also really interested in things like reactive architecture, because they give people a way to do concurrent application building without having to learn too much about concurrency and parallelism. Go also have a reactive binding. It's called RxGo. So you could try that out as well if that helps you build your application in a reactive manner, because reactive in late 2018 to now are all the craze. So a lot of, especially in the Java world, reactive architecture is kind of the next best thing for them now. I don't think in Go community that caught up all that well, because again, Go from the get-go had really good concurrency support, and it made it much easier for people to build concurrent application. But again, if you're interested in that kind of system, you can definitely learn more about RxGo. And this talk, again, was initially created as a 3-hour thing. I tried to condense it. So I'm sure I either went too fast or too slow. I could never probably get it right. But that being said, if you are using Go, if you're familiar with Go quite a lot, this probably was a pretty like a low level talk for you anyway. And if you are new to Go, if you want to learn more and you want to use Go concurrency more, please feel free to reach out. I can like find more resources. We can work together to get everybody up and onboarded into using Go and concurrency even better than they are currently using. With that, I will give the power back to Ari and finish my talk here.
That was really impressive.